thank you all for joining so early in the morning. For me, it's also really early. When I saw it, I was excited, but also I was thinking maybe I can sleep a little longer. So in the next around 50 minutes, we will talk a little bit about how we can use Java 21 and its virtual threads feature to make our code and our application much faster. So a really short introduction to myself. My name is Christian. I've been working as a software engineer for the last 15 years now. I started back with Java 6 and Spring MVC and Java EE. And then 8 years ago, when Angular 2 was released, I switched over to more of a full stack role. And since then, I'm also working in the front end with Angular, JavaScript, and TypeScript. And in the background, I'm still working with Spring Boot, of course, and the whole Spring ecosystem. Now, I'm also a trainer on the side. I give also trainings for front-end stuff, but also back-end stuff. I also do code reviews, and I really enjoy speaking at conferences. I also am a content creator on YouTube, especially about advanced stuff in TypeScript. If you want to get in contact with me, just visit my website, type.rocks. There you'll find my LinkedIn, my GitHub, and also my YouTube channel. And all the code we'll do today, you can also find on my GitHub. So, of course, you can take pictures, but the code is also on GitHub available for you. So if you have questions, you can just ask them all the time. You can go to type.rocks/QA. There you can enter your question, and at the end of the talk, we'll again go through all them. When we are out of time, then I will just answer them later, and you can just go to the page later and see the questions answered. So what we will do today is we will create a Spring Boot application, and we will build this in a blocking manner, and then we will rewrite it into reactive, and then we will rewrite it using virtual threads. So let's get started with blocking, right? So just a quick show of hands, how many of you are still using applications with REST template and REST client, so in a blocking way? Yeah, I see many of you are doing this. Me too, because most of the time we don't have these huge applications which need reactive programming because we don't have that many requests, right? So to honor that, let's just create a simple application. So I will switch over to IntelliJ here. And what I'm using here is Spring Boot and Java 24. Of course, you can also use Java 21 for this. So for this, the first thing we do is we create a new main controller. And what we'll do in here is we will just say this is a REST controller, and we have a request mapping /API. Now, what we will do in here is we will create like a fake web application which you can call and get the information from speakers. So, of course, we will not create like a real endpoint, because then we would have to deal with the Wi-Fi and with the internet. So I will create like a fake REST template which we can use to simulate such a request. So the first thing we do is we make a get mapping. We say /speakers, and we say this returns a list of speaker. Now, what is the speaker? Well, the speaker is just a simple record, nothing fancy, and we say this has just a name. Now, we say here get speakers, and now we want to create like a fake REST client. So we create here our auto-wired, and we have a private fake REST client. And what this fake REST client is just a simple service. So we say here this is a service. And now what we'll do is we'll create like a fake sleep function where we say we can pass how many milliseconds we want to wait. We have our thread sleep here of milliseconds, and we can then use this in our REST client. Now, in our fake REST client, we create a function here which returns a list of speakers, and let's call this retrieve speakers here. Now, what we'll do here, we will just return a fixed list of speakers. So we say we have our private final list of speaker. And we have our speaker list here. And we say we have an int stream, which contains 10 elements. And for each of the indexes, we create a new speaker here. So we have the speaker and then the index here. Now, we could, of course, just return this by using return speaker list here. But what we want to simulate is that when we call our endpoint and we have a blocking REST client or a REST template, then the thread which we are using to access this endpoint will block. So this we will simulate by using here our thread sleep of 1 second. So by using that, when we now go back into our main controller, we can just call return fake REST client retrieve speakers. And now let's start this application. And now let's switch over to JMeter. JMeter is just like an application where you can performance test your endpoints or your application itself. And what we will do is, I will run 1,000 concurrent users at my endpoint. I will have a ramp-up time of 10 seconds, and after these 10 seconds, I will just start to measure the performance. Now, we will do this on our speakers endpoint, so let's run this. Now, what the issue with this is that when we have a Tomcat, we have a thread pool of 200 threads. So this means the 200 first threads, they get handled immediately, but the other ones, they will queue the requests because the threads are still running. So we can see here it's still running. Now, after 20 seconds, we will see this response time. So let me show you the graph. And we can see here, for the ones in the back, it starts at like 1 second, and it goes up to over 3.5 seconds. So the requests get slower and slower over time. Now, why is this the case? Well, the issue is that for each thread we create in Java, also a thread on the operating system gets created. So when you create a new thread by using new thread or an executor service, then also memory on the operating system will get reserved. So let me show you what happens exactly when we do this. So I will go back here and I will stop the application. Now, let me show you a test we will make. So the first thing is we say we have a test. And in here, we will create a list of threads, and we will run them at the same time. So we have a list here of thread, and we say here we have our thread list, and we just say, well, we want to do this for 1,000 threads. And for each of the indexes, we create a new thread. Now, what we could do is we could say new thread, right? But there is also a static function on thread, which is called off-platform. This just creates a normal thread, which we know it for several years now. Now we use here unstarted, and in here we can pass the stuff which the thread will be doing. So we call here safe sleep, so we tell the thread, well, just sleep for 20 seconds. Then we use a toList here, and now we have our thread list for each, and we start each thread. And after that, we just join all the threads, so we are waiting until all of the threads are done doing their work. Now, what we do is, let me open a terminal here. And what I have is, I have a small script here, count threads from Java. This function will check how many threads on the operating system were created by using a Java process. So we can see here currently 72 threads are running. Now, I will use watch here. So every 2 seconds, we run this script again. Now, let's see what happens when I run this test with off-platform. When I run this, we can see that this number will go up to over 1,000 threads. Because we have created 1,000 threads in Java, also 1,000 threads on the operating system were created. So let me stop this. And let's now see what happens when I change this a little bit, and I will do this with 1 million threads. So when we now run this, immediately we'll get an out-of-memory exception. Because the issue is, when we check what the error is, unable to create a native thread, possibly out of memory, because we wanted to create over 4,000 threads, and because each thread blocks a certain amount of memory on the operating system, this will not work. We can see here the stack size is 2 megabytes, so in this configuration, one thread needs 2 megabytes of memory. So this is why we can't just use as many threads. This is why we have thread pools, because when we have one thread, it costs between 1 or 2 megabytes of memory. But when we say we want 1 million threads, we would need between 1 or 2 terabytes of memory to run 1 million threads on our application. But we need 1 million threads to have our CPU usage at 100%. Now you're maybe thinking, well, what is this 100%? Why is this 1 million threads? We have to think about why and what is the thread doing in our application. Because let's think about this speakers endpoint we have. We get the request, then we, for example, queue a database, but during this time where we queue the database, the thread isn't doing anything. It doesn't need the CPU. It's just blocked and waiting. And this short time which it actually needs the CPU is way less than 1%. It's like 0.1%. It needs the CPU only for like serialization and deserialization of our request and response. Now, this is why we need to have many threads so that every time the CPU is available, it's also used, right? So we are now here in the later days of blocking where we say, okay, we have certain use cases where blocking is just not good enough for us because the issue is that we have too many requests and the thread pool is just too small. And this is where we were thinking, well, how can we fix this? We can't just make more threads, so we need to do this differently, and we started using reactive for this case. So let me show you how we can use this to make our code, make our application much faster. So let me switch over here again, let me close this, and we will just go into our main controller, and let's just copy this function, and let's just rewrite this asynchronously. So I will use completable future here, but of course you can use any other asynchronous framework. So I use completable future, wrap this list speaker in here, and let's call this speakers async. Now, of course, what now does not work anymore is our blocking call from our REST client. This is why, for example, in Spring Boot, we use like web client, which is asynchronous. So because of that, we just say retrieve speakers async, and I will create this function. And now in here, we, of course, can't just use thread sleep, because when we are using asynchronous programming, we have to do everything in this reactive chain, in this asynchronous chain. Otherwise, when we use a blocking approach, then this would deny the whole approach we have with reactive programming. So instead of using thread sleep, we use a completable future supply async, and we supply here our speaker list. Now, of course, this would be done, this is not how you apply it in reality. You would just call a web client non-blocking, and this would happen then in the background where it will wait until the response comes back. But what we can do is, we can just add a delayed executor of 1000 milliseconds, and we use the time unit milliseconds here. And by using this approach, we can simulate the same pattern like we have to wait 1 second for the response to come back. Now, with this in place, we can go back into our main controller, and we call this speakers async, and let's run our application here. And we will now do exactly the same test, but we will call our speakers async endpoint. So let's go in here, let's change this to async, and we run this. Now, by using this completable future approach with the Webflux Spring Boot starter, this will allow us to run non-blocking, and we will see a huge speed improvement by using this approach. Because in this case, the thread pool is way too big because we have these 200 threads, but the non-blocking approach will work around this restriction because it's, as mentioned, non-blocking. But let's see the response here. We can see this takes 1 second. And for all of you who maybe cannot use virtual threads or you are on older versions of Java, this here is still a really nice approach. If you have issues with speed in your application, you can just rewrite these certain elements, which maybe are slow, into reactive, and then you can check if your application gets faster. Now, but we were now in the early days of reactive. We were seeing, well, this is much faster, this is much better than blocking, right? But what we also need besides speed, we also need like simplicity, and we need to be able to read our code, right? So let's see what happens when we make this just a little bit more complex. Let's say we want to have not only our speakers, but for each speaker, his corresponding talk. So what we will do is, we will say we have a get mapping, and we have our /talks here. Now, here we have a public list which we return, and this will return talks. Now, a talk here is, again, just a really simple record where we say we have the name of our talk, nothing fancy, and we say get talks. Now, in blocking, we can do this really easy. We just say we have our speakers here. We call fake REST client retrieve speakers, and then we say we map over our speakers. So we have our speakers map here. And then for each of the speaker, we call our fake REST client, and we call retrieve talk speaker. And of course, this is just a talk, and then we map this to a list. Now, let's create this retrieve talk function. This is also quite simple. We have our talk here. We say we want to sleep for 500 milliseconds. So we want to simulate that it takes 500 milliseconds to get the talk for a speaker. And then we just return the new talk here, and we say talk for speaker, and we have our speaker here. Now, we can see here this is quite easy to read, right? We don't have any boilerplate code, all works fine. But even if we only have one user, this request would take 6 seconds because this one here takes 1 second, and this one in our case takes 10 times 500 milliseconds. So 5 seconds, and all in all, this is now 6 seconds. But of course, when we have 100 speakers, then this would take 50 seconds. So what we of course could do is, we could say we change this to parallel stream, but this parallel stream is only useful when you are not blocking, when you don't have I/O stuff, because parallel stream has also a pool of threads under it, and it's always your amount of cores -1. So in my case, when I have 10 cores, you can only have parallelism of 9 threads. So this is not really what we want. And here is what we can use completable futures again. So what we do here is we just create a new get mapping. We say we have our talks async. And now, instead of returning a list, we of course return a completable future of a list of talk. And we call this get talks async. And now it's already where it gets a little bit more complex, because we cannot break this reactive chain. So we have to keep always this completable future running. So we have our speaker future here, and we say fake rest client, retrieve speakers async. And now we call speaker future, and you can see we cannot call map on it, but we have a huge amount of possibilities. And this is just from completable futures. And it's quite hard to understand what to use in which context. Now, in our case, we use then apply. And we say, OK, as soon as we get the result, as soon as we get our speakers, we want for each of the speakers to retrieve the talk, but also asynchronously. So we have a list here of completable futures of talks, and we have our talk futures here. And we say for each speaker, we map over it. And in here, we now have our speaker, and we call fake rest client, retrieve talk async, because we can, again, not use our blocking code. We have to create a new function. So we pass in our speaker here, and then we use toList here. Now, how do we create this talk async? We just say this returns a completable future of a talk. And we can just reuse this code from up here, where we say instead of a list, of course, we just return a new thread, not a new thread, of course, a new talk. And we say here we have the async talk of, and then we have our speaker here. And this only takes 500 milliseconds. But now we are not done, because we now have a list of completable futures of talk, but what we want is a completable future which has the list in it. So what we need to do is we need to do talk futures, map, completable future, and we have to wait until all of them are done and put them into a list. And then we are done. And this is just, if you compare this with this one here on top, you can see it's much, much more code, and it's also not really easy to understand what really happens here in detail. Because this is also not handling errors. So for example, when an error happens in here, we would have to use like exceptionally, handle the error case, and so on. Of course, up here we would also have to do this, but we will do this in a minute. Now, of course, this will be faster, but as mentioned, it's also much more complex. So what is the issue we have currently with reactive? I also use reactive heavily in the front end, like we had the callbacks, then we had the promises with the then chain, and then we went to async await, because this all was way too complex with this asynchronicity. And first, it's hard to write, because we have many different frameworks, and we can choose from them. And because of that, it's also hard to read if somebody else has written the code, because maybe you know like Project Reactor or RX Java, but you don't know completable future. So it's really hard to wrap your head around what is different or what is the same in these frameworks. It's also hard to test. Everyone who tests asynchronous code maybe knows what I talk about. You often need own libraries to be able to take this asynchronous code and somehow make it synchronous that you can test this. And the last thing is also you have compatibility issues, because when you want to have everything reactive until the database layer, the database or the driver also needs to support reactive programming. And you have many different frameworks, many different implementations like RX Java, Vertex, Project Reactor, or even, for example, completable futures in Java. So there are many different problems, I think, in reactive programming. So we are now here in the later days of reactive. We say this is fast, right? This is nice, but it's also way too complex. And this is why the people at Java went back and they were thinking, well, why did we go away from this blocking approach, right? And the problem was that we needed more threads, but it was not possible. So they were looking into it and they were thinking, well, but how many threads do we need? Well, and they saw, okay, we need at least 1 million threads because we need to be as fast as reactive programming. Because when we use reactive programming, then we can use the CPU all the time because as soon as something blocks, then the thread will be available for other stuff, right? So we need to be able to use 1 million threads. Or more if possible. And this is where I came up with the virtual threads. So just a quick overview. When I now talk about platform threads or worker threads, these are the normal threads in Java which also create a thread on the operating system. So platform threads and worker threads, also when you read it like in Java code, these are just normal Java threads. Now, virtual threads, on the other hand, they don't create an operating system thread. They are only a Java construct. And because of that, they are much, much cheaper. They cost like 1,000 times less. They cost like in the kilobytes of memory, where the operating system threads cost like megabytes of memory. Also, they are really cheap to create, really fast, so you can just create them much faster than a normal thread. But why does this work? Why can we create so many virtual threads? And here I show you how this works. Let's think about this speakers endpoint we had. When we enable virtual threads in our Tomcat, what happens is, when we get a request, normally we would use this executor service which has a thread pool. But when we use the virtual threads, it will create a new virtual thread for each request. But the interesting thing is what then happens, because the virtual thread now looks for a worker in a thread pool of worker threads. And as mentioned, worker threads are the normal threads which also have an operating system thread. Now, the virtual thread looks for an available worker, connects itself, and starts doing its job by using the worker as like its tool to the operating system. But as soon as it blocks, for example, we are waiting for input-output, or we have like a thread sleep, it disconnects itself from the worker and moves itself onto the heap. And because of that, the worker is now available to do other stuff. So this means that we can have a really small amount of workers to handle a huge amount of virtual threads. And we will see how many of them we can handle. But as soon as the operating system signals, hey, I'm now ready, the virtual thread can now continue, it looks for any available worker and connects itself to it. And maybe you have spotted it, this is not the same worker. It does not have to be, because it's completely irrelevant if it's the same worker thread or another one. So let me show you how we can create so many threads with this. So I will switch back to IntelliJ, I will stop the application, and we will go into our test here. Now let me open the terminal again, and let's just watch again our threads. Now we can see here we currently have 69 threads running from Java processes, so 69 operating system threads running from a Java process. Now I switched this from off-platform to off-virtual. And we can see here this is still a thread, so we can still use a virtual thread as a completely normal thread. Now when I run this, we will see something interesting. When I run this here, we can see that the number will go up to only like 120, you can see here, like only 50 threads. So this means you can handle 1 million threads with only 50 worker threads. Because as mentioned, most of the time we don't need the normal threads because we are just waiting for input-output. So as soon as I stop this, we can see it will go down back to 70 threads. Now let me show you how this works in detail. So let's go in here, and instead of waiting for 20 seconds, we make an if, and we say if I is 1, so we're accessing the second thread we create here. Then we use thread.currentThread, and we print out what's in there. Now the next thing we do is we have a safe sleep of 15 milliseconds, and let's just copy this 2 times. And now let's see what happens when we run our code, because we will see immediately what's happening with the worker threads. So we can see here we have the virtual thread of the virtual thread 30, so the thread we are working with. But we can see the worker changes each time the thread blocks. So the first time it works on worker 2. Then as soon as we call here our safe sleep, as we call our safe sleep here, this will then disconnect itself from the worker, and then after these 15 milliseconds, it looks for another one. This is worker 10, and then it looks for, it disconnects itself and it uses worker 5. But the thread itself is completely the same, so you don't have to worry about this. Now, let's go back here in our presentation, and let's now rewrite our application from blocking to still blocking, but using virtual threads. And this is really easy because the only thing we do is we go into our application properties file and we say Spring Threads virtual enabled and set them to true. Now we just rerun our application, and what happens when I set this flag in Spring Boot, this changes the executor service from a thread pool to virtual threads. So we can see everything started. Let me switch over to JMeter. Let's clear everything here. And let's switch back to API/speakers, so the endpoint we had issues with earlier. And let's start the test. Now, what happens is we get a request from our speakers endpoint. The executor service creates a new virtual thread. The virtual thread looks around if there is an available worker. It connects itself. As soon as the thread blocks or it's waiting for something, it disconnects itself, puts itself onto the heap, and as soon as the wait is done, it continues its work. So we can see here, we are on the response time graph, and we can see this takes 1 second because we are now using the virtual threads. Now, but what is still the issue we have with this approach? Let's go back into our main controller, and let's see what we still have an issue with our talks here. Now, what we can see here is we did not solve this issue with this slow request of like 6 seconds, because the virtual thread is still just one thread we have. And this will handle this like sequentially, so this still will take, in our case, 6 seconds. And this is exactly where we use structured task scopes. Now, what is a structured task scope? This is really simple. This is just nothing more than an executor service, which we can send our tasks to it, and for each of the tasks, it will create a virtual thread. Now, let me show you how we can do this. We say here we create a try with resource block, and we create a new scope of type structured task scope. Now we can say what kind of results we are awaiting from this fork we pass to it. So we use talk here, and then we wrap everything into it. Now, of course, we are not done yet. What we need to do is we need to pass this retrieve talk function to our scope. Now, how can we do this? We use scope.fork, and we can see here that we can pass a callable, and we receive back a subtask. So we call scope fork, pass our blocking code here, and now we are done to send all our speakers to this scope fork. Now, of course, we can't just return this anymore, because now this is a list of subtasks. So we have to change this. So we say this is a list of subtasks of type talk, and we say we have our tasks here. Now, what's a subtask? Let's go in there. We can see here this is a sealed interface, and we can see, this is the interesting part, this has a state. So each subtask we create can have 3 different states. The first one is unavailable. This means it's still running. There is no result yet, no exception, no successful, nothing, it's still running. The second one is success. So if you have a subtask and you check the state and it's of type success, then you can use get to get the result from it. But the cool thing is also when it's failed, then you can access the .exception function to get the exception which happened inside of the subtask. So you don't have to handle the errors yourself. You don't have to wrap your code into try catch and handle it yourself. This happens inside of your code and inside of the subtask, and you can then handle it when you're ready. So because of that, we now have a list of subtasks. Now we use scope.join to tell our scope, okay, we have sent all the tasks to you, which you need to do. Now please wait until all of them are finished. So we call scope join here. And after this line here, we can be sure that all of these tasks are finished, either successfully or failed. This does not really matter to us, because what we now can do is we call return here, and we can map over these tasks. Because the first thing we do is we use filter, and we filter that we have only the tasks which were successful. So we say if the task state equals state.success, In this case, we want to access it, so we want to map over this, and we want to say use subtask.get to get the result from the successful tasks. Then we use toList, and we are done here. Now, of course, in here, we could also check for exceptions, could see if we would have to do something, if we can still work with this, or if we have to just end the task, end the request here because something happens which we cannot recover from. But this is everything we need to do. Now, you are maybe thinking, well, but this looks quite similar to this completable future stuff here, right? And yes, currently it does, but we have to think about two things here, which, because it's that simple looking, we forget about this easily. First thing is, here, we did not have to rewrite our business logic, because this is still synchronous. And if you have like complex calls, different calls, then you would have to rewrite everything into asynchronous. And the second thing is, here, we don't have exception handling at all. If one of these asynchronous calls fails, our whole stack explodes here. But in this case, this does not matter. But of course, we can make this much easier and much better, because we can extend the structured task scope and can encapsulate our logic. Now, how can we do this? Well, Java makes it really easy for us, because we will just go in there and we create a collection task scope. And of course, we could create a more specific kind of scope, just for example, like a talk scope. But I want to make this like a little bit generic to show you that you can also reuse this for other stuff. So this is also a generic one. And we say we just extend structured task scope of type T. And now the cool thing is we can access a special function which gets called each time a subtask finishes. And this is called handle complete. And the cool thing about this is that we now, every time a subtask finishes successfully or failed, this function gets called and we can handle everything in here. We don't have to do like a filter over all our results in our controller. We can handle everything in here. So let's say we have our private final collection here, and this is of type T, and we have our results. And I will use here a concurrent linked queue. Why do I not use a new array list? Because array lists are not thread safe, and this is accessed by different threads, so we need to make this thread safe. Now, we can also do the same stuff for our throwable here, because of course we could get exceptions. Now, let's make it like this. And in here, we can now say, well, if the subtask.state equals success. In this case, we add this to our result, so we say subtask.get. Otherwise, if it's an exception, we can, as seen before, use the exception function. So we have our else if subtask.state equals state failed. In this case, we just say we have our exceptions, we say add, and we use subtask.exception. Now, of course, we could now check what if we only have exceptions, if we don't have talks, then we will just, for example, throw an error. But in this case, we will not do this. We will only say we return a list here of T, and we say get results. And now we just say return list copy of our results and get this back. And now comes the best part of the talk, I think. Now we can remove some code. Because what we can do is, we can say this is not a structured task scope anymore. This is a collection task scope, which still produces talk. Then we don't need all this stuff here anymore, because we can just use scope.getResults. Also, we don't need this assignment anymore, because we don't filter over this list. And we also don't need this toList anymore, and this map also not. We just need our for each here, because we want to, for each speaker, we want to put this into our scope. So we can make this like on 3 lines of code, but the most important thing is, for me, when we go into the collection task scope, this is so easy to test. You can create a JUnit test or a unit test, then you create your collection task scope, call scope fork multiple times, and you can also, of course, in the scope fork, throw an exception, and you can then check if everything works as expected. So you don't have to use like your own library or something else to put asynchronous stuff into synchronous. You can just use this sequential coding like the normal JUnit stuff you have. So, but let's now see how much fast this is, right? So let's now restart the application. And we will now do a check for the performance. So let's just clear everything. We will go in here and we will change this to /talks. And let's run this. Now, what happens here again is we get a request from our endpoint. The Tomcat will create a virtual thread. The virtual thread will handle this retrieve speakers. Then, when it's finished, it will create a new scope. And the scope will create a new virtual thread for each of the speakers. And with the scope join, we are waiting until all of them are done. And now we have the results. And we call scope results and return it to the caller. So we are now done here. Let's show the graph. And we can see this takes 1.5 seconds, 1 second for the speaker, and a half second for the talks, because they are all done concurrently, so in parallel. So before we go further, just a quick side note about thread locals. Now, if you're only using virtual threads without structured task scopes, they work as expected. They work the same, because virtual threads are just normal threads. You don't see any difference there when you use it in your code. But when you're using virtual threads with structured task scopes, you have to migrate it to so-called scoped values. Now, I will not talk about scoped values today because this will take too much time. But if you're interested, you can go to type.rocks/st. This will redirect you to a DevFox video I did on their YouTube channel, where I talk in detail about structured task scopes and also scoped values. And there you can see exactly how they work. But just to keep this in mind, why does a thread local not work with structured task scopes? Because a thread local, as the name implies, is only working for the current thread. But inside of our one thread, we create a new one by using scope fork. And this is a different thread, so it does not have access to like the thread local from the first thread. So a thread local only works if you have like a thread per request pattern, but it does not work in this case. Also, what are the restrictions we have? The first thing is, if you have synchronized blocks and you're not using Java 24, and you have in your synchronized blocks heavy I/O tasks, so if you're waiting in there for a long time, then you should replace this or exchange this with a so-called reentrant lock. Reentrant lock is also from Java, and they can handle the virtual threads in there. But if you have a synchronized block, then the virtual thread will get pinned onto the worker thread. But they fixed this in Java 24, so if you're using Java 24, you don't have to worry about this. Also, you only have to worry about this if you take a long time in this synchronized block. Tomcat, for example, had the issue they replaced all the synchronized blocks with reentrant locks, and this worked fine for them. The second thing is also native calls. When you do native calls into like C code from Java, then also the virtual thread for this access will get pinned to the worker, because you can do memory access inside of your native calls, and because of that, it would mess up the whole memory frame when you would unattach your virtual thread from the worker. And the third thing is, which I think gets often overlooked, is virtual threads give you no speed improvement if you are using your thread all the time. For example, if you have a thread which does a computational heavy task, then the virtual thread will have no advantage, because it will only have an advantage if you are waiting. But if you are still all the time using the CPU, the virtual thread will not remove itself from the worker, because it's still busy. Now, let's come to the conclusion here. So the first thing is, I think we have reached with this blocking approach by using virtual threads, we now have a real alternative to reactive programming. And I think it's also really easy to do an proof of concept, because if you wanted to do this with reactive programming, you have a bottleneck in your application. You would have to rewrite a huge part of your application in reactive, even until the database layer, to see if this really makes your application faster. But in this case, we don't have to. We can just enable virtual threads and then see if this is working or not, or if we have any issues. Also, what I really like is that it's done in the JDK. It's not like an external library or from an external contributor, but it's inside of the JDK. The changes they made in the JDK were huge. They are supporting virtual threads everywhere they used normal threads before. So to show you this, let me show you a quick introduction here. When we go into our virtual threads, and we go here in our save sleep, and let's open the sleep function here. And in here we have this sleep nanos. When we click on this, we can see that we have this if check in here. if current thread virtual thread, then we call this virtual thread sleep nanos function. And they did this everywhere in the JDK. So they even changed code which was like not changed since Java 1.2, and they made like a pull request of like 100,000 changes in the JDK to enable this. So this is a huge amount of work they put into it, but it's available now since I think Java 19, an experimental version, and it works great. So a huge shout out that they really tried this and achieved this. And I think the most important thing is we have less boilerplate code, because you can see we have these huge patterns to create certain reactive programming styles. And with this, we just have, again, simple patterns, sequential code, and especially with the structured task scope, we can also use it like to run stuff concurrently. Now, just for the structured task scope, this is still in the last preview. So this means with Java 25, this will be out of preview, and you can actually use it without enabling the preview flag. Me personally, I'm using it now for a longer time. But if you want to wait, of course, until it's production ready, then I would suggest you wait for Java 25. Hopefully, some of you can upgrade to 25. I know that many of us are still on older versions. But if you can, you really should give it a try. So we are now here on the timeline and on the new Java 21, where we say we have now reached a point where we like back full circle into blocking, but now with a different twist where we also can use virtual threads. And of course, we don't know what the future will bring us. Maybe there will be another change where we figure out virtual threads are really not the thing. But I think for the next years, we now are really ready with Java to have powerful and fast applications without having to use stuff which makes it hard to reason about. So let's now switch to the questions. We have some of them. None at all. This is, I swear, this stands over. This is, I stand up, I make this, and it's done. I've never used one in my life. Also, when I go to when I cut my hairs, I put nothing in there. Are there any disadvantages to using virtual threads? No, it's not. Maybe it's a little bit of overhead, like 1 or 2 kilobytes per virtual thread, but in reality, this does not matter at all. Because even if you would, so what's also important is to say, never pool virtual threads. So a virtual thread is something that you use once, and then when you're done, you throw it away and create a new one. Never create like thread pools of virtual threads. This is against the whole idea of virtual threads. Next thing is, wouldn't we want to just enable virtual threads by default then? Since no code is required apart from enabling it. Yeah, we can, of course, just enable it, but you have to think about, well, if you enable this by default, maybe there are some real edge cases. I did this talk many times in different conferences, and some people came to me and they were saying, well, we have specific issues when enabling it because we have like, I think they told me they have like 2 terabytes of memory, which they run on different machines, and then certain stuff happens, which is, of course, like this 0.01% of all the people, but nobody has this issue, but you have to enable them because they want to keep it legacy compatible. Are you aware if something like virtual threads exists in something like Go or Python? I think I'm really not a Go or Python, especially not a Python guy, but for Go, I think they also have this different approach with this Go routines, I think, which they can use. Like also Kotlin has their coroutines, which are also now using, for all the people who use Kotlin, they're also starting to use virtual threads inside of their coroutines. So really interesting. But I think every language has its own approach to what they should use. Maybe Python is not the fastest language, so maybe they would benefit from this. But oh, okay. And the next question is, what is the difference, if any, with Kotlin coroutines? Well, the difference is, I think, I'm not really that deep into the understanding of coroutines because I'm not using it on a daily basis. But I think it's like a similar approach, but I can't really tell you the difference right now. I would have to look it up. And of course I can, and I will just add the answer in here later, so you can come back to it. Are there any use cases for reactive code now we have virtual threads? This is a really interesting question because it was also asked in many other ways when virtual threads were created and when were presented. And I think the important thing is, don't just rewrite your reactive code if this works for you. If you have like a large a large code base which works with reactive code and your team knows everything about this, this is fine. You can create great and easy to read code using reactive. But if you have me personally, if you now can choose what you want to use now with a new product or with a new part of your application, I would use virtual threads instead. Yeah, there is a Git repository. You can go to my website, type.rocks. There you can click on the GitHub link, and you can find the code in the list of repositories. I think it's called virtual threads or something like this. Where do we go from here? Are virtual threads the end of the timeline? Currently, I don't think that we will have a change that in the near future, because it took them now I think over 5 years to create these virtual threads, right? So because they want to make sure that everything still works as before. So I think we are now ready to keep it like this. And I have to see if I missed anything. No, I did not. And where we go from here? Exactly. Works with specific If a virtual thread works with a specific scope context, can a worker thread handle multiple virtual threads at one time? No, a worker thread is always connected to one virtual thread, and it uses only this one, and it only can be used if the virtual thread is removed from the worker. So it's always like a one-to-one connection. Which Tomcat version supports virtual threads? I can't really say, I have to say. You would have to check which version. I think they also announced it that they are supporting it. I can't really tell you this right now, but I will look it up and I will add it later to the result here, to the answers here. Are workers equal to how many actual threads are available? Yeah, so normally the JVM or the JDK handles this, how many worker threads are available and how many are used, but you can also configure this yourself. You can say you want to have 100 workers available for your virtual threads. You can do this, configure this yourself, but normally it's how many threads are available for the virtual threads to use. Does the Spring logging MDC work in virtual threads by default? Yes, you have. When you have this MDC logging context, this works, but you have to think of when you are using structured task scopes, and you're maybe having your own context which you pass around, for example, using thread local. Then you should really use scope values because you're using this logging context when you create different virtual threads. What if the fake REST client method has a rate limiter and starts to return HTTP to many requests? Yeah, maybe you would have to check if you have if you know that you can't call your current code with too many requests, maybe you have to upper the limit from this because now it's not that much of an issue anymore. Maybe after some time the database gets the issue, but you of course would have to change this if you wanted to make sure that you also use as many virtual threads as possible. Will this have any penalty for a garbage collection? I don't think so, because the virtual threads are really cheap. And what is the case is if you have thread locals and you use them with many virtual threads, then there are so many instances of the thread locals because they get copied, and this could be a problem with too many thread locals, but if you only have small objects in there, I don't think so. Is it okay to have virtual threads set to yes in a legacy reactor application? Does it collide? So I don't think, I haven't really used it in this context, but I don't think it will collide. But what you have to think about is when you're using reactive programming with virtual threads, then the virtual threads will not have any advantage, because as soon as you're waiting for something which is blocking, then the reactive code will take care of making the thread which lies under it available again. So the virtual thread will basically have no work to do with the removing and attaching again. How do I drink your coffee? With a lot of sugar and with a lot of milk. I think it's just milk and sugar with a little bit of coffee in there. So especially today, I had to add so much sugar because I was just so sleepy in the morning. How does this work with parallel streams? I would not. It works, of course, but I would not use this with parallel streams because parallel streams have when you use parallel stream, the parallel stream itself has a fork join pool of threads, and the amount is always your amount of cores minus 1. So parallel streams are then useful if you are not using it for I/O, but if you're using it for computational heavy tasks, because this is also why you can use parallel threads much better in this case, because personally, I would not use virtual threads with parallel streams when I use I/O heavy tasks. I would use structured task scopes instead, like we have seen in the demo. Can I please send the GitHub repository? Yeah, you can. I will go back to it here. I will go back to it later. I will just, but it's just you can just search on GitHub at typed rocks, and there you find all the repositories. I think it's called virtual threads. So is reactive, we have to finish in 20 seconds. So is reactive and virtual threads same performance-wise? But virtual threads are simpler code given the base is blocking. Yeah, I think this is exactly the case. The speed should be the same as with reactive and virtual threads, but with virtual threads, it's, in my opinion, easier to read. And nice, good question. If I need an assistant, and currently not. But maybe yes, because maybe I'm not that into vibe coding. So maybe I need someone, because I'm also building like a house on the side. So I'm not everywhere with my head. So maybe I need someone, but just for a really small amount of time, and also for free, of course. So okay, yeah. We are already in overtime, so let's switch over to my presentation. And we are in the presentation. So thank you for coming. And if you want to get in contact, visit my website. And if you enjoyed the talk, I would really love if you maybe rate it so that I can see what works and what does not work. And I wish you an awesome conference. Thank you.